So this section now is on the Doppler effect. It's actually the last section in the sound chapter, and we're starting on page 454. So we'll start off with the definition of the Doppler effect. And here it is: the apparent change of frequency of a source of sound when there is relative motion between the source of the sound and the listener. Sometimes the listener is called the observer. I've underlined some key words here. In the definition, we're talking about an apparent change of frequency. It's not real, it's only a perceived frequency change perceived by the observer or the listener. And also, it occurs when there is relative motion between the source of the sound and the listener. So what do we mean by relative? That really means that with respect to each other, the source and the observer are either moving towards each other or away from each other. The classic example of Doppler, you may have seen it, is the classic example is somebody standing at a train station, and as a train is approaching, and a train, this is an express train that doesn't stop. So the train's approaching the station, and as the train approaches the station, the person standing on the platform hears what seems to be a high frequency whistle, and then after the train passes and is moving away from the station, the whistle frequency sounds lower. So it goes from a higher pitch to a lower pitch. And that happens because the train is approaching and then moving away from the listener. Now, for somebody actually riding on the train, that person on the train would not perceive that change in frequency because the passenger on the train is moving at the same speed as the train itself, and they're not either moving away from each other or toward each other. They're both moving in the same direction at the same speed. So there wouldn't be any apparent change of frequency for that listener, only the person at the train station. Now, it doesn't have to necessarily be the source of the sound approaching the observer. It could be a stationary source of sound, and it could be the observer who is moving, not the source of sound. In either case, the Doppler effect will occur. Now, why does this happen? Probably the best illustration is in your text on page 455, figure 2212. So let's do a quick sketch of that. So what we're seeing here is a little dot which represents the source of sound. It's whatever device is putting out a sound. And then we have two situations here. We have an observer over here, and then we have another observer over here. So let's take the situation where the source of the sound is moving to the right, and the two observers are stationary. They're not moving. So the source of sound is putting out some frequency. We'll just make up a frequency. Let's say the source of sound is 500 hertz. So as the source approaches the observer, what happens is that because of that motion, the sound waves are reaching the observer faster than they normally would. And you can see from the sketch in the text, you almost get sort of a close bunching up of the sound waves. And since the sound waves are reaching the observer more quickly than they otherwise would if there wasn't motion, then to the observer it appears the perception is that the wavelength is shorter. So the distance between waves is shorter, so you have a shorter wavelength. And you remember from periodic wave motion, speed is equal to frequency times wavelength, and you can solve for frequency. It's speed divided by wavelength. So if the wavelength appears to be shorter and you're dividing by a smaller number, so if the wavelength goes down, then the frequency goes up. Again, this is only what's perceived by the listener. The source of sound is just putting out a constant 500 hertz, but it sounds higher to the observer because of the motion. Now, for the observer over here on this side, the source of sound is moving away from this observer. And we have sound wave reaching this observer, but because of the source is moving to the right, it kind of stretches out the sound wave wavelength in terms of how long it takes the waves to reach this observer. So this observer is perceiving a longer wavelength. So in this case, a longer wavelength dividing by a bigger number causes the frequency heard to be smaller. So that's what we mean by Doppler effect and why it occurs. And that's why somebody standing at the platform of a train station will hear a higher pitch as the train's approaching, and then after the train has gone by and is moving away, that person will hear a lower pitch because of the longer perceived wavelength. All right, next what we'll do is just introduce the equation that you'll use for solving Doppler problems. Okay, in the text, starting on page 455 and continuing through page 456, is a lengthy discussion which lets you know where this Doppler equation comes from. And there are several versions of the Doppler equation, but we're going to use the final version, which is called the general Doppler equation. And this version of the equation is very useful because it takes into account all the different situations that could occur. It takes into account stationary observer, moving source, or stationary source, moving observer, and it also takes into account the moving towards and moving away. So let's take a look at the equation and then we'll define the terms. All right, so frequency with a subscript O is the frequency heard by the observer. And again, observer is also the listener, sometimes called the observer, sometimes the listener. All right, then the lowercase f with a subscript s is the frequency of the source. It's whatever source of frequency is being put out by the source of the sound. And in all of our equations, or in our problems, we're going to be assuming that the frequency that's being generated by the source is just constant. It itself is not changing, the actual frequency of the source of the sound. All right, the rest of the terms. Now we do have an uppercase V and we have a couple of lowercase v terms. Okay, so the uppercase V is the speed of sound in air. how are we going to get that? In some problems you're just told what it is. In other problems you might be given the air temperature, and then you'll have to calculate from the air temperature what the speed of sound in air is. Now, lowercase v's. Lowercase v with a subscript o, that is the speed of the observer. So is the person who's listening to the sound moving or not, and in what direction? So if you're given a problem where the observer is stationary and just standing in one place, then that would just be 0. And then also v with a subscript s, again the lowercase v, is the speed of the source of sound. And again, you could be given a speed, or you could also be told that the source of the sound is 0 and it's stationary. All right, and then the last thing we need to define here in this equation is a sign convention. We have to account for the fact whether a speed is causing an approaching situation or a moving away. So here's the sign convention that we'll use. That for the speed of the source and the speed of the observer, the sign will be positive for approaching and negative for moving away. Now you will also have to respect the fact that there already are some signs in this equation. So we're only talking about the sign that you would attach to the speed of the observer and the speed of the source. But that doesn't change the fact that we have these positive and negative addition and subtraction signs in there already. All right, in the next section what we'll do is we'll take a look at the example problems in the text.